So, hello everyone. In this lecture and also in this video, I will continue talking about coupled problems. And the focus will be on the solution of coupled problems. Namely, I will talk about the monolithic and staggered solutions, which are connected to time integration. And also, I will talk about the partitioning methods, which are mainly connected to surface coupled problem, and the partitioning would be in space. So, as we talked before, we are working with continuum mechanics, and the mathematical modeling it leads to like a coupled system of partial differential equations. Like in case of thermoelasticity, we would have like a balance equation for the energy. We would have a balance equation for the forces, so the momentum balance. So we'll have several partial differential equations. And then we have also two kinds of discretization. First, we have a domain. So we have the spatial domain. This can be carried out, for instance, using the finite element methods, or if you are like solving maybe fluid structure interaction. Some people go for finite volume elements for the fluid, like domain. It depends. So we would have at the end like spatial discretization. And after the the other discretization is a time discretization. And then we have to deal with differential equation in times, like ordinary differential equations, and then a suitable time integration scheme should be chosen in this case. What do we mean by monolithic time integration schemes? In this case, if we want to go for a monolithic time integration, then all the differential equations are solved in one step and using the same strategy, because it's like putting the whole equations and solving them in the same way. The other option would be staggered scheme, or it's called sometimes partitioned in time. In this case, the equations are solved individually and in a sequential way. So you solve the first equation and then put the results in the second, and you solve the seconds, and so on. We'll talk about this in details. So monolithic and staggered schemes, they are connected to the time integration. And we will talk a little bit about the partitioned scheme in space. And this is based on dividing the problem domain into subdomains. We have seen last time when we talked about the surface coupled problem, we had distinct subdomain or space for the fluid, and also distinct subdomain or space for the fluid, and then we had also the interface. So each subdomain is solved separately, and the interaction between the subdomain and the subdomains is considered using interface constraint in the sense of artificial subsystems. So the constraint would be, for instance, for fluid structure interaction would be related to the balance of forces and the compatibility as an interface. Okay, so let's go a little bit into more details. When we talked about this mass spring system, we had something similar to this. So we started with, or we ended up with second order ordinary differential equations, where we have a mass would be one mass, or the global mass matrix multiplied with the acceleration, which is the like displacement, but with a second time with two time derivatives, plus the global stiffness matrix multiplied by the like vector of unknowns, which includes the displacement of the individual masses. So it is a second order ordinary differential equation. So when we talked about the time integration like a few weeks ago, we did not talk about the solution of second order ordinary differential equations. We talked about the solution of first order differential equations, which are most common. Therefore, we thought about reducing the order of this ordinary differential equation to order 1. So the system can be reduced to first order by introducing the velocity vector. So we add a new unknown to our system so that the system become not second order, but first order ordinary differential equation. So the velocity is simply the time derivative of the displacement. And we introduce this as a new variable. Then this equation can now be written in this form. It's exactly the same. it's equivalent. So, but we have now a new mass matrix, which includes the global mass matrix and identity here on the diagonal, because we have now u dot and v dot. So it's this vector y dot. So this is a new formulation. Plus, now we have a new stiffness matrix. It also includes this identity because we have now the velocity here. So, and then multiplied by y, which collects now the displacement and the velocity as a new unknown vector, and then equals to p, which represents like the forces that we have. Now we can rewrite this in different ways. Now we just inverse the mass. So we have now y dot equals to minus m minus 1 k y plus m minus 1 p. So it's a vector valued equation, and it has exactly the same form as we have seen before. So first order ordinary differential equation of the form y dot equals to f t y. And we could have also some kind of initial conditions like velocity at the beginning or displacement at the beginning. For this form, the usual schemes for solving ordinary differential equations can be implemented. So exactly for solving first order ordinary differential equations, we have talked about the implicit Euler, explicit Euler, trapezoidal rule, BDF2, and so on. So these are schemes, they can now be implemented for this form of equations. Now, if we want to talk about monolithic schemes, now all the equations are collected now in this form, and therefore we call this monolithic because it's a direct solution and all unknowns are collected in one vector. And then if we apply a scheme, it will be applied to all equations because they are already in the global mass matrix, global stiffness matrix. So in this one-step schemes, as example, implicit Euler can be implemented, and the whole system will be solved in one step. The other scheme would be then the staggered time integration scheme. So it's a kind of alternative. In this case, we need also to reduce the order of our ordinary differential equation from order 2 to order 1. So we start with the force balances of the three mass system. So we have 1 mass, 2 mass, and 3 mass. We have seen this in I think in the previous lecture. And then we have a global global balance equation. And then n would be then referring to which mass. So if we say n equals to 2, it means we are talking about the second mass. So we have 3 masses. It means we have also 3 balance equations in this case. To reduce the order of the equations from second order to first order, we follow exactly the same idea. We introduce a new unknown vector, which includes the displacement and the velocity as the first time derivative. So it's u1, v1. For each equation, we follow this scheme. So we have y2 as the second unknown vector, and y3 is the third. So we have now we change the variables, and then by including this new idea, the system of coupled equations, which are 3 ordinary differential equations, they are now of first order. The first equation would be then y1 dot equals to fy, and it includes the unknown. So it includes y1 for the first mass, and y2 and y3 for the second and third mass, because it is a coupled problem. So each equation includes information from the other equations. Then we have here also y2 dot and y3 dot. So we have these 3 equations. If we want to follow monolithic scheme, then the 3 equations will be solved in one step. But now we are talking about the staggered time integration scheme, so we will solve these equations in a sequential manner. So in the staggered time integration scheme, we can apply similar or different time integration scheme to the individual equations. Most of the time we follow the same time integration schemes because then we have the same order of error, and then and also the implementation will be easier. Let's take, for instance, the implicit Euler, and we apply this to each of the equations. Let's apply it for the first equation, which is y1 dot. In this case, we have on the left-hand side y1k plus 1 minus y1k. So we discretized our time domain into like n time step, and then each time step will be delta t from tk to tk plus 1. So we have here, as I said, on the left-hand side, we have y1k1 plus 1 minus y1k divided by delta t. On the right-hand side, it's an implicit scheme. So we write all the variable in the current time step. So it's every one of the variables will have the superscript of k plus 1. So we have y1 k plus 1, y2 k plus 2 k plus 1, and y3 k plus 1, and so on. And even the force can be written in the current time step. So it will be p1 k plus 1. And for simplicity, we just write f1 k plus 1 because we know it's an implicit. We apply the same idea, so the implicit Euler to the second equation and to the third equation, then we have exactly this form. Okay, so how the algorithm look like? So in the implementation, we start with some initial values. Usually, first time step, it will be the initial state of the system. If we have no deformation, then initially, then y1, y2, and y3 will be 0. If you have already started the computation, the known values are the values from the previous time step, which we have already computed. So they are our initial values in this case. And then if our problem is like force derivative problem, so we are updating the force at each time step. And then by updating the force, we have to compute the corresponding displacement. So it would be y1, y2, and y3 vectors. So the second step, so we start with the initial value, we put predictor values. So we need a predictor for y2 and predictor y3. Why we need this? Because in the first equation, we have also y2 and y3, but one equation can give us only one unknown, so which is a y1. So therefore, we need some initial values for y2 and y3, because otherwise we cannot compute this y1. And this is what we are doing here. So the third step, we take the first equation, which we have already discretized in time. Y2 predictor and Y3 predictor, they are predefined, so we know them. And then we update our force, which is also like a kind of boundary condition. So this is also a known value because this is what we are like giving. And with the only unknown, then will be y1 k plus 1. It's one equation, one unknown, and we can solve this. It's like in a straightforward manner. Then we move to the second equation. First equation will give us y1 k plus 1. This can be plugged in the second equation. And for the second equation, the only unknown will be then y2 k plus 1. And for the y3 in the second equation, it's the predictor value and the updated force as usual. They are known. Then from this, we can compute this y2 k plus 1. Now we move to the third equation. We have computed y1 k plus 1 and y2 k plus 1 from the previous two steps. Then we can compute from this y3 k plus 1. After solving these three equations, we can check the convergence. Usually, this is corresponding to the errors or to the value of the residual. If our residual giving us some values below the tolerance, then we have a convergence. Otherwise, if the error is still big, it means we have no convergence. Then we have to make this in an iterative manner. So we update our predictor values by putting the resulting y2 and y2 k plus 1 and y3 k plus 1 as a new predictors. And then we compute y1 k plus 1 again, and then we continue this loop until we get the convergence. When we have the convergence, it means we have yes here, then we can update the time step. So we have like this second loop, which is related to the updating to the time step. Then we have tk plus 1, so our new time equals to the previous one plus the time step. This is a very rough description about the algorithm, because, for instance, there's a software which you are applying flexibly. There's also a time adaptivity. So if you apply this iteration like several times and you are not getting the convergence, automatically reduces the size of the time step so that we can get like faster conversions. So it's a time adaptivity strategy. It means delta t can be changed also, but in this presentation, I'm assuming that the time step is a kind of constant. We update the time step, and then we update the variables. Now the computed variables, they are known, so we call them now yk, and our new unknown then will be this yk plus 1. So the new yk would be exactly the yk plus 1 from the previous time step. And then we go to step number 2. It means we put this here as a predictor, and then we continue with the same step until the time becomes the final time, and then the computation will be terminated. Okay, so this is how the staggered scheme like works. In the FlexPD, as we have seen in the exercises, you are writing the equations in somehow strong form. So if you put between the equations then, it means the software automatically understands that you want to go for a staggered solution. So it takes the first equation, solve it, and then put the results in the second, in the second equations and make this iterative computation. If we don't put then, so if you write the equations without this then the software will understand that you want to go for a monolithic solution, so you want to solve the whole equations in one step. And there are a lot of details in this connection. So sometimes you have to go for a monolithic solution scheme because staggered scheme might be not stable due to the high degree of coupling. We will address this in other contexts, so especially in the context of thermoelasticity. And there will be in the exercise some tests of the issues. So some by playing around with the material parameters, you can change the degree of coupling, and then you will see that in some cases you have stable solution, in other cases you will not have stable solution. Now we move to this third scheme, which we have talked about. So monolithic and staggered, they are connected to time integration. Now we are talking about the partitioning methods in space. Now it's not particularly for the time integration, it's about the space. And the partitioning schemes are, as I said, it's very important, especially if you have fluid structure interaction, because you can solve the fluid in different solver and in different strategy, maybe on different computer, and the solid or the structure also in other scheme, but you have to make sure of the compatibility. So if we recall the 3 mass with 2 springs system, partitioning means it can be represented by this way. So we go to the second mass, which connects the the left subsystem and the right subsystem. So we cut this. It's not necessarily to be M2 divided by 2. It could be any ratio, but this is the representation which I'm applying here. So it's a virtual cut because the interface is still there. And but we have here to make sure that at the interface we have compatibility and force balance. It means that the interface forces are consistent with the Newton's third law, which is action equals to reaction. So we have a balance on the interface, and then we have a kind of compatibility because at the interface or the material point at the interface, they belong to each of the subsystems. It means the displacement at this point for the first subsystem and the displacement at this point for the second subsystems exactly the same. And this displacement can be represented by ZF equals to U2, which is the displacement of the middle mass. So we have now separated this system into 2 subsystems. It means now we can apply different balance equations for each of the subsystems. So this is the first balance equation, and this is for the first system. As you see, it's the second. It's the ordinary differential equation of second order because here we have a vector of acceleration. So we can follow then in the solution the same way by reducing the degree of the ordinary differential equation to be, for instance, of first order. For the second system, we have exactly the same. We have second order ordinary differential equation. And then, as you see here, we have the forces, and then we have some other like terms which come from the interface. So this is the interface actions. Then we have to apply or to consider the constraints on the interface. So we have the interface palette, so the force which comes from the first subsystem and equals to the force which comes from the second subsystem, or action equals to reaction. So we have a palette as the interface. And then we have the compatibility condition, which tells us the interface kinematics is consistent. So the displacement as the interface for the first subsystem and for the second subsystems are it's exactly the same. So if we say that psi1 is the displacement of the first subsystem, it is equals to the interface displacement, and the displacement of the first subsystem psi2 equals to the displacement at the interface. Okay, so this is like a general introduction to this issue. I will address this in more details when I talk about the fluid structure interaction, and then I will specify these terms in maybe in more clear way. I will also give you a reference where you have like more details about the discussion of coupled problem, especially this one. This reference was already mentioned before, but I will mention it again in the future with this. So with this, I'm at the end of this video. Then we'll meet on Monday, and then until then, I wish you a good time. Thank you.